Hello, everybody. I am Linda Hutchinson, and I will be presenting our project on acoustic classifiers for non-invasive citizen science monitoring of the Leach's storm-petrel. And the authors are myself, Dr. John Kearney, and Dr. Cindy Staicer. So, a little bit of background. The Leach's storm-petrel is a small nocturnal burrowing seabird that was recently uplisted from vulnerable to threatened in Canada, and it has two distinct calls: the chatter call, which is emitted by both sexes during flight and in the burrow, and this is what it sounds like. And the purr call, which is exclusively emitted within the breeding burrow between mates, so it is indicative of breeding. And this is divided into two subcalls, the breath and the rattle, and this is what that sounds like. And there the breath comes before the rattle. Unfortunately, the most common current monitoring method is invasive, and it involves reaching your arm into the burrow and handling the birds. However, the storm-petrel is a candidate for non-invasive monitoring called PAM, which involves leaving a recorder in the environment for an extended period of time. The problem with this method is that it produces an immense amount of data to analyze. A solution to that problem is the creation of acoustic classifiers, which are computer algorithms that can extract target species vocalizations from recordings. So the research question we asked in this study is whether PAM and acoustic classifiers can be used for the non-invasive monitoring of Leach's storm-petrels. To answer this question, we deployed 18 AudioMoths recording units on Bon Portage Island from the 1st to the 22nd of July. They were programmed to record from 11 p.m. to 4 a.m. First, we set them up along 3 distance transects to see how far from the burrow purr call could be detected. Then we redeployed them in plots of known density to look at a possible relationship between burrow density and call rate. Here you can see a picture of an AudioMoth recording unit placed at the opening of a burrow. In Figure 1, you can see a map of the island, and the orange marker indicates the place where we deployed the AudioMoths. Now, for our analysis, a subset of the recordings was annotated manually using Raven Pro. Annotation is when you manually go through a file and select each target call, and then the program can give you information on the number of calls and their acoustic parameters. This subset was then divided into training data and test data. Training data was used to train Kaleidoscope Pro software to recognize and extract the storm-petrel calls. We created 3 classifiers, one for the chatter and then one for each of the purr subcalls, breath and rattle. The test data was then used as a benchmark to test the performance of the classifier. Finally, the 2 classifiers that performed the best were used on the entirety of the recording set to examine factors in influencing call rate, such as occupied burrow density, date, time, and weather. The performance of each classifier was assessed using 2 metrics, recall and precision. So, what did we find? We found that purr calls were not able to, recorders would only be able to pick up purr calls from less than 2 meters away from the burrow entrance. Looking at Table 1, the recall of the classifiers in the test files indicated that they were extracting about 40 to 65% of the storm-petrel calls within that recording. The precision of the purr call classifiers was moderate, indicating that they were correct in their identification of 33 and 50% of the positively identified calls. However, the precision for the chatter call classifier was 95%, meaning that it was almost always correct in what it extracted. Looking here to Figure 3, we see that throughout the 17-day period of the density study, the average temperature generally increased the precipitation remained at or close to zero, and the wind speed was relatively low. However, on July 10th, the wind speed spiked to 48 kilometers per hour, which coincided in a dip in call rate of both of the call types. But this could just be because the wind was far too loud for the recorder to hear over. The per call rates varied, with the higher densities generally having the highest values, and the chatter call rates from all the burrow densities seem to follow the same general pattern. As expected, the control plots had the lowest values for both call types, indicating that the data was fairly reliable. Looking to figure 4 now, we can see that throughout the 5-hour nightly recording period, the average temperature decreased. The precipitation was low again, and the average wind speed generally declined. The per call rates of different plot densities varied throughout the night, again with the highest being at the highest densities. Over all the densities, there was a general upward trend of per calls throughout the night. As in Figure 3, the chatter call rate by hour seemed to follow the same behavior regardless of density. Overall, the chatter classifier performed the best and should be the one used to reliably isolate storm-petrel calls. Weather did not seem to be strongly associated with call rate trends. The general vocal pattern of the storm-petrel chatters was consistent regardless of density, making them a potential tool with which to identify new Leach's storm-petrel colonies. There does seem to be an association between burrow density and per call rate, although the recorder needs to be exceptionally close to the burrow to determine breeding status. So we conclude that PAM has potential as a storm-petrel monitoring method, but further study is required to build on these findings. Thank you. And we would like to acknowledge the team at Acadia University for their support: Dave Shuttler, Phil Taylor, Riel Hoig, Taryn Muldoon, and Tristan Sanderson, as well as our team at Dalhousie, Alicia Kirkwood, and Elizabeth Mack. And we would like to also thank the funders of this project, the David and Faye Soapy Foundation, and John F. Kearney's Listening Together project.